All right, good evening, ladies and gentlemen. My name is Mitch Kane, and this is my project. I used convolutional neural networks to classify NASA images. Some information about me. I have an applied mathematics degree from the University of Rochester, and I've spent the last 9 weeks in the galvanized data science immersive. I recently left the Marine Corps after 5 years, and I've always wanted to work at NASA. So when this project came along, I jumped at the opportunity to use some data sets that I pulled from NASA. But the problem became that as I tried to pull things from the NASA API, it became clear that their images weren't very well sorted. And so that became my project on its own. The data sources I used are NASA Images API, VGG16, which we'll talk about more later, and I Googled 3 images of pizzas from Google to try to trip up my All right, so this is the kind of image I got when I pulled. At first, I used the API to scrape to get the URLs, and I just kind of used the get command, get requests to pull the images down onto my local computer. And this is the kind of images you get when you do that. You can see, the first one's planet, clearly not a planet, and it's kind of hard to tell from this image, but it is a bunch of people playing instruments in an orchestra. They're playing hosts of planets. So this is not a particularly good image filtering system that NASA has in place. I ended up pulling a little bit over 1,300 images for this project, and this wasn't great. So I had to go through and I had to hand classify all of them. There are a lot of images in there that are hard to classify, like this one, especially for a computer, is a woman in a lab. But there's also she has a planet over her Bunsen burner here. So this would be classified as a planet image, but there are things in this element that would trip up the neural network. So my solution was to build a convolutional neural net to learn what a planet was and classify whether or not there was a planet in the picture. My first network had 3 convolutional layers and 3 pooling layers. It was trained on 453 images and validated against 150 images, and then I upgraded it to 1,100 images and validated against 200 images. And after 15 epochs, it achieved an accuracy of 76%, which is pretty good, but not great, and was very overfit. If you notice, this graph all the way to the right shows that we minimized the loss on the training set, but our validation loss kept increasing the entire time. So building our own convolutional neural net didn't end up being the correct answer to the problem. So, okay, never mind, let's borrow somebody else's. I used the Visual Geometry Group Model 16. It's a pre-trained on a vast library of images from ImageNet and has 13 convolutional and ReLU layers, 5 pooling layers, and several fully connected layers. It takes a while to train, but it's good. It's easy to adapt to what you need. It's from the Oxford Institute for Large-Scale Robotics, Oxford Robotics Institute, and it was for the Large-Scale Visual Recognition Challenge of 2014. And its architecture is this. So once we trained on those same set of images, we ended up getting a 92.5 accuracy on the validation set, and no major overfitting. If you notice, the validation loss and the training loss both trend downward throughout the entire epoch, all of the epochs. So we ended up by putting in these random planets, images rather, and the classifier successfully classified this pizza as not a planet, Neptune as a planet, this pizza as not a planet. This one kind of tripped it up a little bit, classifying it as a planet. The next steps are to conduct analysis of the test set. I do have an additional test set, but I wasn't able to complete the run of the prediction before this presentation. Once that analysis is completed, we'll give it additional training data to try to limit false positives and potentially start training it to identify different planets, nebula, and spacecraft, and then hopefully get hired by NASA. Are there any questions?